So anyway, so I think what we will do today is to the first few minutes. We will go into where we were in virtual recovery, and then we'll open the session for about 1 hour, 15 minutes for the question and answer. Okay. So I'm here with you to answer your question, whatever I know. There is absolutely no guarantee that I know everything. And I should not really know everything, to be honest with you. If you know everything, it means that you are a fool. Because nobody knows everything. And what we know is very little than what we don't really know. Okay? And what we also something very, very important for you, which I have learned with experience. And NMR fits absolutely well with that. You know, there is an equilibrium. We all are chemists, biochemists, molecular biologists, whatever. There is an equilibrium between learning and forgetting. Honestly. So, for instance, learning and forgetting, right? And it's a reversible process. If you read, learn, try to gain knowledge, the equilibrium is shifted towards learning. If we don't do that, it is shifted towards forgetting. Never forget this thing. You know, you're designed inherently to learn. And if you don't learn, you forget. So it depends on what is your choice of where you want this equilibrium to be shifted. Okay, I was telling everyone that there is an equilibrium, and you all know as a chemist that equilibrium means that there is a reversible reaction between product and substrate or whatever, and this equilibrium can be shifted towards product or substrate, right? So there is an equilibrium between learning and forgetting, between knowing and ignorance. Okay, so if you work on learning, the equilibrium is shifted towards learning. You know more. And if you don't learn, the equilibrium automatically goes towards forgetting. So always remember that learning is a process which not only you need for new knowledge, but you also need for keeping that knowledge which you have. If you don't do that, you tend to lose this knowledge. Okay. So going beyond philosophy, we today as the format, we will have plenty of time. Don't worry. If you don't have any class, then we can spend a bit more time. And I know few languages except Arabic and French. I know a little bit English. I know Urdu. I know a bit of Pashto as well. I just like it. And Saraiki, of course, I know. And Gilgiti, no, I don't know. Shina, I don't know. Leela has never tried to teach me. So you can ask me questions in any language. Okay. And if I know, I'll give you answer in that language. Otherwise, I'll give you answer in English. If I understand your question. Okay. So remember this fascinating world of modern NMR spectroscopy. Happy people, we should remind you that it's all about nuclear spins. Nuclei are magnets, small little tiny magnets because they have protons. And therefore they have magnitude and they have a direction. Magnets are vector. In the absence of static magnetic field or applied magnetic field, they are randomly arranged, they are degenerated, they are totally wild, they are everywhere. And because there is no difference literally in their energy, so they are just on all directions. And you can't do much with it. You place them in magnetic field, which was initially in 1940s was a permanent magnet. Remember you used to play with magnets? It was a permanent magnet. And when you place these magnetic field, these tiny small magnets of your sample, remember you're not isolating nuclei. You can't do that, right? This is your sample, and your sample, most likely in a liquid phase, is placed in the magnetic field, and when you place them into magnetic field, which is called B naught, magnetic field density flux, it's also called static magnetic field. Static means that it's constant magnetic field. Then magic happens. Some of these tiny little nuclei align themselves, or some opposed to those. That polar magnets, spin hockey. And when they align themselves, and some are non-aligned or opposite to the magnetic field, two energy states created. Two energy states created. One is low energy state, the other is high energy states. Luckily, there is a tiny little excess of population in low energy state. There is small little tiny excess, slightly more population in low energy state, which is called net magnetization. The difference in population is also called Boltzmann distribution axis. Okay, and that is what would absorb radio frequency. And when you give radio frequency, these net magnetization vector will absorb and it go to the exciters. This is the absorption spectroscopy. Very easy concept. Okay, so this was a concept which everybody was learning who was born in 1940s. And life was so easy. You can hear songs of Umar Kulsum and Lata and Rafi and whatever. And they can live with it very nicely, no issue. But all of a sudden, somebody has thought that, number one, that this difference in magnetization is this different population should really increase because we want to increase the sensitivity. So physicist solution was to develop electromagnets. Electromagnets. Electromagnets are the magnets which are magnet because of electrical field. All on ports and shippings and motors and all that, these are electromagnets which are used to big containers and all that. These are just electromagnets. So when electromagnets were used, magnetism was increased. As a result, the difference in energy between the lower and high energy state was increased. And when there is a difference increases, the population difference also increases. Because jumping between low and high would be difficult. The barrier of jumping is more difficult as a result. Then it was a very easy also. Nobody really, thank you so much. Nobody was really unhappy. Everybody was happy. Because it was just a magnet. You invented a magnet. We got no sense between there. Then all of a sudden, they realized that No, recording is absorption of radio frequency. And you know the radio frequency absorption because when you place this magnet, tiny small little magnets of nuclei, they process in magnetic field, they process. It's called Raman frequency. And these protons, that's the example of a proton, are different precision frequencies depending on B effect. Any confusion about B effective? If there is any, we can clear it. Don't worry, just ask question. If there is a confusion, let me tell you. If there are 5 protons and they all are different, they are only different because it's not that the static magnetic field is different. Static magnetic field will not the same for all of them. They are different because they have different electronic environment. And electrons have an opposing magnetic field. So when you have more electrons, you have more shielding. When you have less electrons, less shielding. And when there is a more shielding, means that you have less be effective. The local magnetic field with that proton is feeling is slightly less as compared to a proton which is completely exposed, has very little electrons or something like that. Okay, so they have a different Raman frequency. Since they have a different Raman frequencies, they absorb radio frequency differently because they have to match. It's called resonance. And this is what chemical shifts. You know, this is the chemical shift. Why different protons appear in a different position? Because they have different Raman frequency. And absorption of radio frequency is your way to read Raman frequency. How would you read our Raman frequency? Without absorption of radio frequency, you cannot read it. You should have something external to read it, you know. So radio frequency, which is applied perpendicular, is called B1, is absorbed. And so you get these 5 signals, and these 5 signals are chemical shifts. And these chemical shifts, you read these chemical shifts also, and this is what chemists are interested in. Chemists are absolutely not interested in magnets. They're not interested why helium is put over to who cares about electromagnetism. They don't even interested about what is going on with the protons. Right? Who cares about protons? We just want to see signals on the table, on a piece of paper, right? And so what? But you know, they were the beneficiary of physicists' hard work. Physicists have done really very, very hard work. And to create and establish a very large NMR spectrometers, and eventually they developed superconducting magnets because they thought that if magnetic power, electromagnet has a limitation. I mean, how much electric current you can pump in? You cannot really pump indefinite electric current. It will burst, evaporate, right? But then develop supermagnets. Physicists were so curious. They developed superconducting magnets, which is again a magnet, but you put them into very cold liquid, very close to absolute zero, minus 269 Kelvin or minus 268 centigrade or whatever. And then when you place them in liquid helium, so remember there is a relationship between temperature and conductance. The lower the temperature, higher the conductance. You also the relationship between the resistance and temperature. The lower the temperature, the lower the resistance, right? Yes. Okay. So they developed the superconductor, and sensitivity went skyrocketing. Chemists had to pay bit more money for it, and that bit more money was. But you know, they were not very happy because recording of absorption was a time consuming. And it's just a very simple and proton NMR and C13 recording. Nothing else you could do. You just have proton, you give radio frequency in proton, and then one by one they are recorded. So you spend about an hour and you record one spectrum. Okay. If you're looking for C13, you have, how can you distinguish your sample has proton and C13? How would you selectively record proton without seeing any C13 in absorption? How can you selectively detect elements without interference of the other element? It's Raman frequency. And Raman frequency for proton is very different, 4 times higher as compared to C13 or nitrogen or oxygen or chlorine or fluorine is different. You know, you just tune. It's just you have 5 different radio stations. Okay, from low field to high field, from FM to AM or I don't know. So I need to hide this thing. You don't understand? Fine. Okay. Atya is laughing. It's growing like animosity. Okay. So they have 5 radio stations, and one is C13, nitrogen, etc., etc., etc. Okay. So if you want to listen, Radio Sana or Cairo, City Cairo or whatever, or Yuande 1, okay, Khartoum, etc., or Radio Gilgit, or Radio Dera Wadi Khan, or Peshawar, Banu, whatever, Karachi, FM. You need to tune radio frequency. You go to that radio frequency and you would listen only that one. Okay, exactly the 5 different elements. You need to match the Raman frequency of that element. And when you match the radio frequency of that element, you will not listen any other radio. You will not listen the signal and song of C13. You will not listen the song of nitrogen, oxygen, or whatever. So you have this tremendous capacity of selecting one element in the presence of other element. You cannot do that with UV. Can you do that? Can you say, okay, I want only the non-bonding proton electrons of carbon and not hydrogen? No. IR, can you say that I just want the stretching between carbon-carbon but not between carbon-hydrogen? Can I do that? Mass, can you say that I just want carbon-carbon bond cleavage and not carbon-proton bond cleavage? Or in X-ray, can you just say that I want only nitrogen and not carbon electron density? Can I do that? Only NMR spectroscopy can do that, right? So they were standing, changing, they get spectrum. So it was so time consuming that a crazy chemist somewhere in Switzerland said, okay, why we need to do that? Why we need to just stand and scale this absorption one after the other? Why we need to go one by one and then record a lousy spectrum in which we have a lot of noise? And he said, I want to have a different approach. I want all these protons to be excited at the same time by a pulse, a burst of radio frequency broad enough to excite everyone. Understand? Broad enough to excite everyone. It's called pulse power. Turning on radio frequency and turning it off. The duration of turning off and turning on is a flip angle where you want to make it work. So he said, I want to excite everything together, and I would only record relaxation because I know they would relax differently. Why they would relax differently? Because they have a different hour frequency, they have absorbed differently. Though you have given a radio frequency pulse, but they have selectively absorbed what is matching with them. So each one of them was differently, so they were relaxing. He said, I want to excite everything together by a pulse, and I will record relaxation. Okay? And I will record relaxation. It will be much easier because I can excite. Because the absorption was taking so much time. Now you excite them in fraction of a second, and then you turn on your detector and you record relaxation. And that where this was a problem, this was the time when problem for you started. Because now I need to understand pulse. You need to understand where this magnetization vector representing the difference in population goes with pulse. Right? And here the excitement of NMR started also. Because now you play with it. It was never possible on the face of the earth that you can record except simple proton NMR, C13 NMR. Now, with that pulse, everything becomes possible. 2D, 3D, 4D, 5D, 6D, multidimensional. It was all become possible. The world opened for you. When world opened for you, at the same time, you need to understand how this world is. What are the contours? What are the theory of that world? And this is the reason this NMR course is uniquely different. No one in this entire country teach you about the NMR which you learn today here. Because people never want to go into it. Their theory starts from Raman frequency, absorption, and signal. Again, and ends on signals. Here we are trying to learn this magnetization vector, which is M0, the bulk magnetization vector representing the difference in population, Boltzmann distribution axis, M0. When you give a radio frequency pulse and the duration of pulse, power of pulse define which element. Okay? Power of pulse define which element. For C13 is different, for proton is different, for hydrogen is different, whatever. The duration of pulse will define where this magnetization vector will go. Okay? So you bring it on XY plane where your detector is. Now the world is open for you. The world is open for you now because first time in the history of the world, you know these tiny little nuclei, where they are on XY plane. In UV, do you know that between low energy orbital to high energy orbital, where it goes, how much time it takes? There is no absolutely way that you can check that dynamic process because it's just so absolutely fast. Right? Here, NMR is different again, that you can take this magnetic field and place it anywhere on three-dimensional coordinates. If we give 90, if we give a pulse duration, it can come on XY plane. If you give a little longer, it goes into minus that, right? If you give a little longer, it can come to 70. If you give 360, it goes up, right? So you can place this magnetic vector anywhere on XY plane. You can play with it because you know how to play with that. And that is what NMR make me excited because not very much, a little bit I know how to play with it. I know to some extent how to design NMR experiments, little bit. Though I have never done it, but I know what I need to do to place. If I have proton, nitrogen, oxygen, I want to play with all three of them together. Can you do that? Could you do that at the time of absorption spectroscopy? No. Now you can do that. You can have radio frequency. I'm not confusing you, just telling you the truth. You can have radio frequency for proton. You bring it to XY plane. Then you bring radio frequency for C30. Give a 180 pulse. It goes down. Then you bring radio frequency to nitrogen, right? You can play with all three pulses, one after the other, and let them interact with each other to become heteronuclear experiments. You know, so if Egyptians are playing a football match with each other, it's not a competition. Not very exciting. If you can bring Cameroonians, which are good in football, if you bring them on in the field, also by another pulse, you can see more excitement. And if you can bring Sudanese to interfere in this, to sabotage everything, it becomes even more exciting, right? You can only do that with pulses. Okay? You cannot do that by the old experiments. Okay? Understood? Amna is minding it. Okay? So this is the basic story of, and then I told you that the simplest experiment on the face of the earth by pulse NMR is one pulse. If you wish to record proton NMR, okay, you give 90 pulse, right? You record FID, wait for a while, it goes back to thermal equilibrium. You give again 90 pulse in proton domain, and you do it like 16 times or 32 times. You record 32 FIDs and 16 FIDs. You have 32 or 16 spectra. You get a good signal to noise resolution. Just one pulse. Easy life. Similarly, C13, you can do that. In C13 domain, you become radio frequency. You tune your radio to C13. You bring it to 90 XY plane. You let it relax. Turn on your detector. Get the FID. You get a C39. And you can do it nice slowly. It's not so fun, you know. I mean, of course, you get this tremendous increase of signal to noise ratio, which was the main advantage why pulse was developed. You get this tremendous because instead of one, you're recording 16, 17, 30, 100, 200 spectrum, scanning, right? Pulse again, pulse again, pulse again. You get signal to noise ratio, which is chemists were always interested in it. But chemists were also very, very interested to know what happened between relations between proton and carbon and short range, long range, couplings between protons, coupling between proton and carbon, coupling between nitrogen and all that. They were all interested in it. Chemists are very curious people, right? But they don't want to work. They make physicists work for them. They just tell them, I want this. Easy. And then physicists, very hard work, they keep doing it. And at the end of that, they say, okay, it's not so good. Improve it. So thankless. Okay. So once this pulse was developed, they said we would like many other relationship between these elements in my molecule. Because in order to understand my molecule, I'm not only interested in proton, because my molecule is an organic molecule, the framework is carbon, right? So I know about carbon also. Physicists say, okay, you record carbon spectrum. Then he said, no, I want to know how proton and carbon are related to each other. Or I also want to know which proton is interacting in long range with other protons, nosy, in space. And physicists said, what to do with that? So they developed multiples NMR experiments. The easiest example which I showed you was the pulse was playing with the pulses, okay? And the easiest, most beautiful example to understand multi-pulse experiment, let's say two-pulse experiment, to begin with. From one pulse to two-pulse experiment was inversion recovery. And inversion recovery is not only for you to understand how these pulses are. I'm blocking your view. Okay, so it's not that that you know how these multiple pulses work, but also a very important information about spin lattice relaxation. You can calculate how much time it takes to relax from full inversion to thermal equilibrium. So T1 can be calculated. And this is a very simple experiment. This is the pulse sequence. Okay. And it's so easy. So now you want to calculate T1 relaxation time for every proton in your molecule. You know why T1 is important? T1 is important. Of course, there are many other applications also, but T1 is important. Because you see, if you do not know how long it takes to fully relax back, you're giving a wrong second pulse. You know, assume that you're recording 32 skein proton n. 32 skein proton n. And your magnetization vector is not fully recovered to thermal equilibrium. And it is somewhere here. If you give a 90 pulse, where it will go? Below X line say. And every time you do that, every time you will do it, you have more error. So it's very important that you should be able to calculate T1 so it relax back completely before you give a second pulse in simple proton. So T1 calculation is very important because without T1 calculation, you cannot really record successful NMR because every time, if it is not 5T1, in NMR rule of thumb, you give 5T1 time, so they relax back. You want to make sure that they are on Z, all of it. Because if it is not Z and it is little less than Z, then 90 pulse will bring it to below the X-ray plane. And again, next time, this will go even below. So the error will accumulate. So T1 is very important. 5T1 you can only calculate when you know T1. Right? Yes. Right. Okay, so T1 depends on, it's called spin electricity. It means that the energy which you have given radio frequency, we have given to as a pulse, will go to somewhere. Okay, where it will go? It will go to solvent molecules which are around. Lattice means environment. It will go to the in the neighboring. It will go into solvent molecules. If you have slight impurities, it will go there. If you have solid particles, little bit, it will go there, but it will go into environment. Go into environment. And what are the factors? Which is a very, very important. You see, the T1 depends on their inherent capacity. I'm not confusing you, but inherent capacity of how they are capable of transferring energy. Every proton is different. As if you excite them some together, it's called longitudinal relaxation, how this energy will transfer. And remember, in the world of physics, the energy never transfer like this. Energy always transfer when there is a resonance. So it means that solvent molecules, the other dissolved oxygen, others should really match with their frequency. Only that energy will be transferred. So it depends upon it depends on their capacity to transfer. The rule of thumb: the molecule, if the molecule is tumbling, tumbling, move back. If the solution is viscous, then T1 is small because tumbling is less in viscous solution. If solution is non-viscous or less viscous, then tumbling is hard. The T1 relaxation time would be faster. So it depends on many factors, including if you have undissolved particles. If you prepare your sample without filtration, let's assume without filtration. If you have this sample without filtration, you have solid particles. Absolutely wonderful thing for energy, because they can absorb energy as much as you want. So T1 depends on many factors because the energy is going into X-ray. Now, I just conclude by saying that this 2-1 experiment is that you give 180 pulse, you inverse it, you bring it to the X5 plane, it is on minus that, right? Minus that. But it would not remain on minus that, you know this, right? It has to go back to plus that. And from minus that to plus that is T1. Isn't it? Right? Largely T1. How would you measure it? You cannot see this. You cannot see this whole frame of reference. How would you measure it? So you give a second pulse. And you give a second pulse and bring it on XY plane because you can only read what is on the XY plane. Your detector is on XY plane. So you need a second pulse. Okay? Okay, so this is your thermal equilibrium, your initial state. In NMR, it's called perturbation. When you give a pulse, it's called perturbation. You're disturbing, perturbing. So you bring it 180 Hz pulse, invert, right? You can't read this. You cannot read this signal because your detector is on XY plane. So immediately after 180 pulse, if you give no delay, if you give 90 pulse, it will come on XY plane. Okay? XY plane. So when it will come on XY plane, you record FIT. Okay? One experiment finished. Second experiment, you get 180 pulse, wait for a while, and when you wait, this will shrink because a part of it will go to thermal equilibrium side. And when you give 90 pulse, you record FID, another experiment finished. Okay? So this is the experiment and time. Okay? And time. And time means that then you give a third experiment. You give a 180 pulse, you wait a bit more. The delay is a bit more. And delay is a bit more, it is shrinked more. Okay? And you give 90 pulse, you get FID. And then you give more delay, eventually it will come up, start coming up. Now 90 Hz pulse will bring it to Y, plus Y, instead of negative. And eventually, from full negative signal to full positive signal, how much time it will take? Delay is your T1. This delay is your T1 because this is how long this system has taken to relax back. Okay, so this is called inversion recovery. Inversion, fully recover T1 time. How would you read it? You need a second 90 pulse. If you don't give a second 90 pulse, you cannot record it. And you get a spectrum like this. Let's say 0 or 50 microsecond, you get a full negative signal. Because 90 Hz pulse gives you -5. Okay? 1 second from microsecond to second, you know this, you're increasing the time. Every time is a different experiment. Remember, there is not one experiment. You cannot do that in one experiment. You have to finish the experiment by recording FID. Then you give another 180 pulse, you wait for a while, you increase this time, and every time you increase the time, you get a full positive signal. From full negative signal to full positive signal is your T1. And how you record it? You record it by 90 Hz pulse. Now, I think there would be a confusion. Okay, so The detector is here. Beautiful eyes. It's nice eye. Like it? Okay, make it a bit big. Face, nose. Okay, that's okay. So the detector, if it is here, if your vector is here, if your vector is here, the FID starts from here. Okay. If there is any confusion, it's called phase. This is critically important for you to understand. Detector C positive phase. Okay. If okay, so important. If and the signal would be after FID, signal would be like this. If your vector is here, the detector will start looking at. Okay, this is the starting point, and the signal would be okay. So that is how your detector can distinguish where this magnetic vector is. If you can ask a question, if it is here, it can be anywhere, right? I don't know why I'm not able to make a good vector. It's like spaghetti. If this is like this, the detector will see okay, and the signal would be distorted. If this is like this, the frequency would be absolutely no reason for you to worry. The only thing which I want to tell you that if magnetic vector, if detector see it right in front, you get a positive signal. If it sees back, you get a negative. Okay, and that is how you see this. Okay, is exactly if you're a detector, Adil, and I am a signal in front of you, big signal. It's slightly big. Wonderful. You see me like this. Okay? Happy? Okay. If I turn to minus x, what do you see? Shoulder, shoulder, right? If I go to minus y, if I turn like this, see me from here, right? When I come back to you, you understand? When you turn on the detector, Adil, and you mean, Adil would see me differently, isn't it? You can't see me all the time if I'm on XY plane. Not exactly the same, right? So this is exactly what happened, and called inversion recovery from 0 second all the way to this second. Whatever the full recovery is called inversion recovery. For if there are various protons, the T1 time will be different for different, but slightly different, not so much different. You don't need to worry about it. Why you need to worry about it? You just want to have approximation of T1 time. Because if you don't know a T1 time, you cannot design a good NMR experiment. Only when you know T1 time, then you wait for 5 T1, then you give a second pulse, and you can. So this is the reason why inversion recovery, number one, this is an excellent first experiment with 2 pulses. The second is, it's also used, it's not useless. It is used for estimation of T1 time. So for instance, you can see the treatment time 3.2, 3.4, 3.3, 4.8, 5, 3.8, 3.2 is relaxation because these protons have a different relaxation time. That is the reason they appear different FID. So if you really want to wait for it, I would go for 4.8 maximum T1 and wait for 5 T1. I'll wait for about 22 seconds. And then I'm absolutely 100% sure that everything is on Z. I mean, I can't be more careful than this. I am using the longest T1 time and then waiting for 5 T1 to make sure that that everything is on thermal equilibrium. It is on Z. And then I can give, so this is the reason that all NMR spectroscopists actually, after a periodic interval, they calculate T1 time. They want to make sure that the experiments are okay, because if T1 time is not properly calculated, there can be error, you know. So this was an inversion recovery. Now I am fully available for question and answer. And in that case, I liberate myself from these buttons.
I have a question related.
Every question is welcomed. The more question you ask, the chances of going to Islamabad is fully paid air travel. And this is for all, everyone. Okay. Thank you. Okay, so yes, Adil.
For the T1 is different for each element. The T1 is different for each element. For when we do carbon 13 NMR in Egypt, they ask me how much time you need to 2 hours, 4 hours. How can I define my sample 8 hours?
Okay, so that has nothing to do with T1. That is number of scale. So if your sample is less, then you need more scales. Remember, if you have sample if you have just 1 milligram of sample for C13, you naturally need more spectra in order to have improved signal to noise ratio. And that would take 1 hour, 2 hours, 3 hours, sometimes overnight. They run experiment for 7 days, 4 days, 3 days. Days. Same sample. Keep scaling to improve the signal to noise ratio. But T1 it has nothing to do with you. The NMR spectroscopists who are running the experiment must know about it. If they don't know about it, how would they calculate when the next pulse has to be given? Okay? So this is called calibration of NMR spectrometers. Often it is done automatically now in new NMR spectrometers, but sometimes they take a standard sample and calculate.
Yeah.
So a rough estimation of T1 is required. You don't need to be that sure. I'm telling you that T1 time is important. In MRI, and not to confuse you, in MRI, you don't record frequency, you record T1 for different protons, water protons. And then you make a map of T1. Because brain has lots of protons, millions and millions and zillions of protons. I mean, of course, they're water, but they are in different environment. So the MRI is a T1 map. Okay. And at some point of time in 1980s, some crazy chemist, they said, well, why we don't need to worry about frequency. They actually tried to use T1 time as a chemical shift. You understand? Instead of having frequency, they said, okay, why don't we just measure the T1 time or relaxation time? Each proton has a different relaxation time, therefore it is as good as frequency. So instead of making large tables of frequencies, why don't we make tables of T1? Methyl T1, this one, CH2 T1, this one, OH T1, this one. Okay? So for instance, in ethanol, you have 3 frequencies. Some crazy people in 1980s, they were saying, I don't want to waste time on FID or on Fourier transformation. It's enough for me if I know frequency FID time. How much time it takes to relax methyl, how much time it takes to relax CH2, how much time it takes to relax OH, and I can use it as a interpretation tools. But you see, it didn't really work because, to be honest, chemists were working with frequency since long, and they were so habitual about frequency. So they said, okay, no, we would like to stick with the frequency. ppm, delta value. We don't want to go into this crazy T1 business. Other question? Yes, sir.
So if I run the same experiment on different machine, like 400 megahertz, 600 megahertz, or 800 megahertz, what things should be constant and what's changes things, and how to calibrate it?
Of course, you need to calibrate every machine. But the difference between 400, 600, 800 would be that as compared to 400, the 800 is a larger magnet. Okay, it's about 19 Tesla Okay. 18.5, 18.2, 18.5 Tesla. Tesla is magnetic power. So more magnetic power, more energy difference. More energy difference, more population difference, more sensitive. So if you have the same sample, 400, you may need about, let's say, 200 skin. In 800, you may need about 50 skins because already population difference is high. Time would be less. Okay, less scaling is required because already the population difference is so big enough that the signals are already strong. Any question? If you ask me a question which I don't know, I'll be very happy. Because then I can go read and come back. Yeah. No, your turn is next. Can someone volunteer? Anila, you can be volunteer. You have to run. Okay, thank you.
Thank you. For me, I want to know the comparison of the benchtop NMR is 60 megahertz and let's say 200 megahertz of this other domain.
Okay, good question. You know that people in the developing world are getting poorer and poorer and poorer, and so they don't go for a big magnetic machine now. They are buying benchtop. Benchtop, you know, you have seen NMR. They're not right like rocket launchers. They are huge machines. They are of human height. You need to ditch. You need to make a hole in order to make it stubborn and all that. They are damn expensive. You know, they're in billions of dollars. Benchtop you can buy at 60,000 USD, 70,000 USD. Still not cheap. But benchtops are the same machines, but smaller one. They cannot be superconducting. Remember, they cannot have liquid helium, they cannot have liquid lithium because that need levels. These are permanent, these are electromagnets. These are electromagnets, therefore they have a limited magnetic field. It can't be like 300 or 400 or 500. Okay, so number one, the magnetic field is less. The cost is less also. So they're good enough. You can be happy person. If you're working on, let's say, you know, if you get something in 10, 20 milligram or 30 milligram, or you're working on synthetic chemistry, where you can synthesize you synthesize compound in large quantities. You don't need to worry about that because it simply means that that you can record it. The quantity is not a problem for you. So that machine is good enough for you. The big machines are required when you have little samples and you want to do lots of other experiments which you cannot do on benchtop machines. You know, pulses are, and benchtop also pulses, everything is safe. But of course, sensitivity is lower. So it is good enough for if you have sufficient quantities, large quantities. Okay, next. Yes, sir. Who is?
Thank you, sir. My question is also still around the power of the magnets. But first, I want to ask you, were saying something about filtering sample. Filter sample before analysis. Is it when samples are not much soluble in solvents, can it be filtered before analysis?
Yeah, you should filter. You should always filter. Even if you're sure that it is 100% soluble, nothing 100%, right? So if you're sure that it is absolutely soluble, then you still filter, because if you have solid particles in your sample, is that you would waste so much time, because T1 will be like this. The FIDs would finish. FIDs would be like this. Not like this, but because there's so much solid particle will absorb energy. So it'll be so easy for the system to go back to thermal equilibrium. So it's important that you filter it. And for certain experiment, such as nuclear magnetic resonance spectroscopy, NOE, which you use for geometrical confirmation analysis, the signals are so tiny that you need to degas that also. You want to make sure that there is no oxygen particle is there. You want to degas that you put a vacuum to make sure there are no gases in the soluble part of your molecule, right? So because dissolved gases are also good sink for absorbing energy, T1, right?
So the second one, sir, what is the effect of this energy difference in terms of 300, 400 megahertz and 800 megahertz? What effect does it have in the splitting pattern? Does it mean that if we analyze on higher instruments, we have fine splittings in terms of doublets of doublets? I think I was told that if you do some experiments on lower instruments, some particular protons that are supposed to be doublets of doublets will remain as doublets. Is it?
Very good question also. Number one, the difference between 200, 300, 400, 500, 600, 700, 8, 1.2 gigahertz or whatever, the more magnetic power, the larger energy difference, large population difference, more sensitivity. Sensitivity increases, right? But with the magnetic power, resolution also increases. What you're talking about, resolution, it's not that you want to see the signal. You also want to see splittings, because splitting gives you very important information about coupling. So as far as N1 type of couplings are concerned, 300, 400, 500 are safe. When it comes to long range couplings, fine splitting, W coupling, 1,3 coupling, these are couplings of different kinds. Then this fine small resolution is more and higher magnetic. Okay, so if you are very much interested in resolving your signals to a very high level of resolution, then you spend time on larger machines. But you see, at some point of time, you need to say, okay, my spectrum is good enough. Why would I go and remember? The time of 800 is more expensive than time of 300. You know this. Why it is different? Of course, the running expenditures are, but at the same time, lifespans are same. Lifespan of 300 megahertz and 800 megahertz is same. Of course, running, cost, everything, but also to mention that on 800 megahertz, you run 100 experiments, and 300 megahertz, you also run 100 experiments in the entire lifetime. In the entire lifetime, which is more expensive? 800. You know this because you spend more money and you got the same results. So you don't really go for unnecessary. You never go for high magnet experiments. It's like a GP, general physician of your neighborhood, right? And going to a very specialized doctor in Aachen. Whose time is more expensive? Same 800 megas. They are 800 megas. They're so expensive. I generally don't go there. Yes, madam.
Always we are speaking about still I am around.
Okay, I think we'll come to online participants also. I think now will handle that. Yes.
Sir, I'm still around the T1. Always here you are give example of a compound like this. T1 is important and this factor affect like solubility, purity, and something like that. If our sample is protein, and this protein is very sensitive, so sometimes it denature inside the NMR tube. So T1 will affect also, right? In this case, that means we will exclude this protein from the experiment, like, or we need to centrifuge it, or what we will do.
No, we have other ways of doing things also. For instance, denature because of what? Heat. So you cool. You know, in all these NMR machines, you have refrigerator. You can cool it until you freeze the solvent. You don't want to freeze the solvent. You know? Before freezing the solvent, you can cool it. And you can heat it also. A lot of experiments are required for heating. You know, all this tautomerism and confirmation analysis, one chair form to the other chair form, heating is required. Similarly, cooling, if it is denatured because of thermally unstable, you cool the sample. And there is a reason why cryoprobes are used. Cryoprobe means, you know, gases, helium cooled probes. So, and you can do the experiment with better sensitivity. You can cool the temperature to, let's say, if the ambient temperature is about 25. NMR always work normally on room temperature. Your NMR tube is in room temperature. Although 3 centimeter away is minus 269. Okay, but this insulation is so high that your NMR tube is at room temperature. And if at room temperature the protein is denaturing, you would decrease the temperature to 20, 15, 10, unless it freezes, you know. And you don't want to freeze because if you freeze, then experiment gone. It's not solid state NMR, it's liquid state.
Sir, online XMR.
Okay.
Why 90 pulse is more powerful in rotating a sample in XY?
Why 90 pulse is more powerful for rotating?
In rotating a sample in XY plane.
You know, because if you have M naught at Z, and you want to bring it to the XY plane, it's 90 pulse. So it's not powerful, it's useful. Okay? Because you want your magnetization vector to be on XY. Okay? Good.
For online participants, I have given you right to unmute, so you can speak with sir as well if you wish to.
Online participants, you can speak also. No, okay. Yes, I can start.
Then how on resonance frequency. Because most of the molecules have
Which factor?
E factor, how effects on
T.
G. E factor effects on resonance frequency. E factor.
Magnetic field? Okay. Magnetic field. Very good question. Thank you. I am so happy. You see, magnetic field. Magnetic field, right? Magnetic field, you increase from 200 to 300 to 400, 500, 600, 700. Okay. Their Larmor frequency also increases. Several things happen. You have more magnet, greater the energy difference, greater population, more Larmor frequency. So the frequency would also be different. But you get the same spectrum. On 800 and 200, you get the same chemical shifts, right? Chemical shift the same. Because you divide it by the magnetic power, by the magnetic power, megahertz, you divide it. When you divide it, the chemical shift of 800, 200, 300, 400 would be same. You understand? Yeah. So Larmor frequency is different in 800, 200, 300, 400 because it increase with B naught, right? Increases B naught. But in order to see your spectrum, because you don't want to see the spectrum of the same sample from different NMR spectrometers differently. You want to see exactly the same spectrum, better resolved, better sensitive. So you divide the Larmor frequency with the operating frequency of the machine. When you divide it, the factor is same. Okay. Thank you. Good question. Rainy. Okay. You're getting close to you. Some of you have actually reached Hyderabad. It's still about 1,200 kilometers away from Islam. It's not reversible. It's just that you don't want to go to these places alone. Well, of course, there's nothing wrong in it. People are very hospitable, but you are aiming for Islamabad. Everybody is aiming for Islamabad. Okay. Next. Yes, sir.
सर हमें जो पल्स हम ऑब्जर्व करते हैं वो एक्स वाई प्लेन पर होती है जब ये इक्विलिब्रियम पर आता है तो वो जेड पे जाता है सर जेड पे तो हमें पल्स ऑब्जर्व ही नहीं होगी तो हम किस तरह देखेंगे हमारी पल्स है या नॉइज है पहले हम डिफरेंस ही नहीं कर पा रहे उसके बाद उस जगह पर हम अपना एग्जैक्ट टेबल पे किस तरह फाइंड करेंगे
Okay, so the question is that it's not pulse, it's bulk magnetization vector. I'm not, right? You're talking about magnetization vector, right? So she's saying that magnetization vector, when it goes to Z, how would you observe it? Very logical question. You only observe it by giving second pulse and bringing it to the 90 XY plane. This is the reason why inversion recovery has two pulses. Remember that whenever it goes to minus Z or plus Z, you cannot read that unless you give a second detectable pulse to make it detectable. And that is 90 pulse. So you bring it to XY plane and you read it, okay? Again.
सर एक्स वाई पर आ जाएगा ना तो हम एग्जैक्ट जेड का टाइम किस तरह सर जेड पे आपने कहा कि सबसे ज्यादा T1 होता है तो हम वो किस तरह कैलकुलेट करेंगे
Very, even Z. It's not from minus Z to plus Z is T1, right? About 63% of the relaxation is equal to T1. So you inverse it to minus Z, right? 180 pulse. And from minus Z to plus Z is T1, right? And you want to measure it. This is what you want to do. How would you measure it? This is your question. So you record many experiments. Okay. So you record minus that, no delay, and you give 90 x pulse. When you give 90 x pulse, it comes to minus 5. Okay? You record one experiment. Then you give a delay. Delay means you give some time before you turn on the detector. And during this time, the magnetization vector would never be same. You know, it's a dynamic process of reversing. So when you give, let's say, 1 second, the magnetization vector is straight. It is going back to up. Then you give a 90 x pulse again. You bring it to minus 5. You record FID. But this FID is going to be different from the first FID, right? Because it has shrinked. And then you keep doing it, then at some point it's 0. Because half up, up. And then it starts going up on plus direction. When you give a 90 pulse, 90 x pulse, it comes on plus 5. So your detector starts seeing the same signal positively. From full negative signal to full positive signal is T1. A good question. So from full negative signal to full positive signal is T1. And how would you measure it? You cannot measure without 90 x pulse because your detector is there. Unless you bring it to XY plane, you cannot detect it. But during this delay time, the position of this vector is different. And this is fundamental concept in 2D NMR spectroscopy. Also, 2DB largely delay का ही मसला है. वो आपको बताएंगे. बिल्कुल ऐसे है कि it's like this, you know. All these guys are playing, or girls are playing on in football team. In football, okay. And Adil has taken the ball and going to Cameroonian post for scoring, right? You have detector is a camera, okay? You record Adil, okay? After some time, you have another photo of Adil. Adil has moved forward, right? And then you keep recording it unless he goes to the Cameroonian post. Plus that, right? So you need to bring it to camera. And your camera is detector that requires 90 x pulse, okay? So it's a dynamic process. The last question. Last 2 questions. But I think some people have their classes every day. It's okay if you want to, or you have classes. Okay.
Sir, what is the effect of hybridization on chemical shape? SB1 and SB2.
Okay, chemical shift is dependent on 5 factors. Number 1, most important one, shielding deshielding. Okay? Shielding deshielding means electronegative atom, electronegativity or whatever. Okay? Number 2, hybridization. sp3 hybridize a more electron around it. sp2 is less, right? sp is even less. Okay. Second is hybridization. Third is magnetic anisotropy. Because things like benzene or triple bond or something like that, they have a localized electron field, right? And this localized electron field would have a dissymmetrical interaction. The fourth is temperature. The more temperature, it would affect on chemical shift also. Okay. Fifth, I don't remember. Honestly, so I'll give you that. I know it's 5 factors. Huh? Which one?
Yes.
No. I don't remember. I'm a human being, so.
Like hydrogen.
Oh yeah, thank you so much. You got close to Sakkar. Okay, hydrogen burning. Hydrogen burning is also affecting chemistry. The more hydrogen burning is stronger, the more deshielded. Okay, thank you.
Okay, sir. The same related to the same question. Sir, SB less electrons, but sir, spherical. Mean SB1 hydrogen hybridization is more downhill than SB2 and SB3, but SB 50%. It can shield magnetic field or not.
Okay, so his question is very brainy also. Theoretically, SP3 shielded, SP2 somewhere in between, SP is here, right? But you know, problem with SP1 is especially when it comes to triple bond. Acetylene is very crazy. Acetylene triple bond has a magnetic anisotropy which shield proton instead of deshielding it. Okay, therefore they often come somewhere between close to shielded. You understand? But this is the reason why it's not straightforward or linear. Magnetic anisotropy is a factor. So SP in acetylates. This is acetylate. You can see that? So this the electron is shielding it. As a result of it, it doesn't come close to benzene. It comes close to somewhere, 3, 4, something, shielding it. Okay, more question? Yes.
Now we have this. I want to know about if you give this 90 pulse for the sun. I want to bring it to X and Y. So if I have this plus 90, so which one is best? Y or X?
No, it depends on, yeah, okay, good question. He's saying that, XY plane, there are 4 coordinates, right? Plus X, minus, plus Y, minus Y. And lots of in between. Okay? You want to respond? So it depends on radio frequency pulse. Okay? So right hand thumb rule. If you want to bring it to, you have your radio frequency on X, it will go to Y. Okay? If you want to bring it to minus X, then you need to give pulse from Y. Okay? If you want to bring it to minus Y, you need to give the pulse from minus X. So you can place it anywhere.
That means change the direction of the pulse.
Yeah. Radio frequency pulses you can give from any side. And how can you practically do that? Radio frequency pulse, how can you practically give it from any side? Practical solution, hai na? This is a problem practical because this probe has wires and you can use any direction of the wire to give pulse. Okay? So you can give pulse from anywhere and you know where it will go? By right hand third group. Okay. That is again NMR. No other experiment, no other technique would give you such a flexibility.
Here we draw this p-axis. We have here is a picture in X. So why the signal is started on negative, not on positive?
Okay, so okay, your detector is on Y, okay, and your magnetic vector is in front of Y. It means that you see a positive signal start from above. Okay. If your detector is on X, but signal is on minus X, it will start from, it will see me from here. Back, not my face. Okay. And same with on different direction. You don't need to worry about that because in rotating a frame of reference, we always start either positive or negative. We don't want to have a distorted signals, which is now half up, half up, down. You don't want that. You want either up or down. For instance, this is practical application. How many have you seen depth 90? Seen that? So you know that CH2 come down. Okay? This is a practical application of this. Because you bring CH2 to minus Y. And you cannot do that without knowing where it goes and without rotating frame of reference. Okay. Any other question? Someone has gone close to Saka. Someone gone close to very down.
Sir, yes, in ethanol, signal of CH2, methylene protons. There are two possibilities, either doublet of quartet or quartet of doublet. How can I know? Means splitting first by proton of OH or by CH3.
Okay, good question again. Is asking a simple question that the CH2 is going to be splitted by CH3 and OH, not or, both CH3 and OH. Only if your OH is visible. If you're recording your ethanol spectrum in a solvent in which OH is deuterated, then you see splitting of CH3 only. Okay, but if you're recording the spectrum in DMSO or you're recording a neat ethanol, then you would be able to see this splitting of CH2 both by CH3 and OH. Okay. Now the question is whether it's going to be 4 CH3 plus 1, 4 plus 1, or it's going to be first CH3 split and then OH split. I don't want to get into it also because I think it's just premature. We will discuss this later. Because I don't want to confuse you because this departure from N1 rule is different. Okay, everyone. Tomorrow we'll meet again at 10:30, and can you arrange for them tea, coffee? No, tomorrow.
Sure.
And maybe one falafel or samosa or something. Okay. Thank you.